Hello and welcome everyone to the fourth episode of AI Insights, which is a series created by the European Center of Excellence in Exascale Computing, research on AI and simulation-based engineering at Exascale, or in short, CoE RAISE. AI Insights aims at shedding some lights on the research that we're performing in the project by the different partners. My name is Andreas Lintermann. I'm from the Jülich Supercomputing Center from Forschungszentrum Jülich in Germany. I'm coordinating this project, and I'm also the host for today. In the last three episodes, we already had a look at different topics. So in the first episode, we met with Fabian Hüpenthal from RWTH Aachen University, talking about AI for turbulent boundary layer flows. In the second episode, we met Professor Maurice Riedel from the University of Iceland, who was talking about our unique AI framework, UAIF. And in the last episode, we met with Jeva Tim Rothe, who was talking about the educational service portal that we provide to the community. Today is with me a new guest. Yeah. So, by the way, if you would like to have a look at the other videos, yeah, there should be a link on top and also a link in the description. You can, of course, find it. Yeah. So if you're interested, please go there. So today with me is a new guest. Yeah. So let's continue with you. His name is Cristóbal Samaniego. He's from the Barcelona Supercomputing Center in Spain, in Barcelona, and he is a recognized postdoctoral researcher over there. And he's also a lecturer at the Ramon Llull University, where he's teaching in giving lectures in statistics and also in mathematical analysis. Cristóbal is working in work package 3, yeah, of CoE RAISE, and that deals with computer-driven use cases towards Exascale, and more specifically, he's working in task 3.2, which deals with the development of AI technologies for a wind farm layout optimization. So this is something that we will learn about today. So welcome, Cristóbal.
Thank you very much, Andreas. Good morning, all that are seeing us. Thank you for the introduction. For me, it's a pleasure to be here because we talked before, I really love to talk about the details about our work. So I think that this is a very nice project. So I'm glad to be here. Thanks.
Yeah, welcome. So maybe before we completely dive into the technical details of the things that you're doing in this task, we also want to learn a little bit about you. So when I hear your name as a German, I could imagine, okay, this guy is coming from Spain, but you're not, right?
No, I'm not coming from Spain. I'm coming from Ecuador.
Oh, that's quite a long distance. How did you make your way to Spain then?
So the whole history is very long, but more or less I can summarize when I received a call from Guillaume Musso. You know Guillaume Musso. Guillaume Musso is right now my boss, and they offered me a PhD, so I accepted immediately because it was in a topic that I really love, so fluid and structured interaction. But I have to be fair and to say that before called with Guillaume, I knew Mariano Vázquez. Mariano Vázquez also worked with Guillaume at Barcelona Supercomputing Center, and he liked my profile, and we started to talk a lot when I met Mariano. So it was a great opportunity to come to Spain.
Where did you meet Mariano? And
Mariano, I meet that's the good question. I met Mariano when I was studying my master's degree with numerical methods in Ecuador. So we invited Mariano to give a class about fluid mechanics. So I met him there. We talked a lot. I really expressed that I wanted to continue with my studies in computational mechanics, but especially with the high performance at Barcelona Supercomputing Center was the place for me. I am a computer science at the background.
Yeah. So your background is engineering, I guess. Yeah. You studied
computer science.
Okay. So this is something that you started studying in your hometown, right? In Quito?
Yes, in Ecuador. Also, my master's degree was in Ecuador, and Mariano was a guest there. So we invited to give this course, and this. I think that all the story at this point. I met Mariano, and after that, 3 or 4 months after that, Guillaume called me and offered me that position. So it was very nice for the for part of these two guys. I really thanks all the time, all my life for this opportunity because they trust me, and I hope not to disappoint it.
And is this something that you always wanted to do? I mean,
already
as a child or in school, you had already a feeling, I want to do something
complicated
really. With mathematics, things like that?
Not really. You know that when, I don't know if, for example, you know the curriculum of a computer science guy. So normally, solving partial differential equation, knowing about physics is not the main focus in a curriculum of this. But when I was studying computer science, I received some courses about it, especially the solving partial numerical differential equations with computer. So I really loved. Then I decided to not to follow the traditional computer science things, but to study something about physics, computer science, to mix computer science with physics was something that I really love. So I decided at that moment when I received these courses to study computational mechanics. Yes.
Okay, that means there was some point in your life that you worked on your problems, and then you thought, okay, you met Mariano and learned about maybe the Barcelona Supercomputing Center with all the huge and big machines that they have. So you decided to go big in your PhD, yeah, to think about bigger problems that really need high performance computing systems to solve.
You know, something that was very, very curious, I didn't tell you, is that, for example, in my master's degree, I was the only guy that studied computer science, because it's not a normal thing. But at the end, it was a good thing because it's numerical methods. It was a master's degree in numerical methods, so you have to code a lot. So at the end, so at the beginning was like very hard for me because physics, in a general point of view, it's not so easy for a computer science guy. But at the end, when you need to code, people, for example, from my master degree, wants to join me because I knew how to code the methods. So it was,
I completely agree with you, Cristóbal. Yeah, you know, I also studied computer science and came into.
I didn't know that.
Computational fluid dynamics. Yeah. And I have to say, it was also very difficult for me to from this, let's say, very theoretical topic dealing with all the numbers and let's say theoretical computer science, going to this field where there's more physics involvement. Yeah, and we really have to understand the physics, and then, of course, from this go to the numerical part, how to implement these things to solve these partial differential equations that you talked about.
Okay, but you study computer science or no? Sorry,
I studied computer science. Yes.
So you live the same things that I lived before. Okay, nice.
Nice to know.
I didn't know that. But you know that something that I find that it was not so bad is that I learned physics in a general point of view from the beginning.
Yeah,
it was not so bad because it's like learn in the right way from the beginning. So it was hard, but it was the right way from the beginning. So, for example, my partners at the study, yes, in another sense, with some simplification, was sometimes hard for them.
Yeah, for me, it was a little bit different because I already finished my studies in computer science and then jumped into the cold water and went to all lectures from my doctoral father. Yeah, so, and this was all about computational fluid dynamics, yeah, and fluid mechanics. So I had to learn a lot during my PhD, but I liked it a lot.
I like it a lot also, yeah. For me, it was at this moment when I was studying my master's degree, it was the moment that I decided to pursue the high-performance computational mechanics. So that was the moment. So I decided I wanted.
And then as a PhD student, what was the topic of your PhD student?
My topic was fluid and structure interaction.
Okay, that was in the context of the things that Mariano usually does with the simulation of the heart.
It was a Guillaume project, but you know, at this time, Guillaume and Mariano works very close together. So, but it was in the context of a European project also. So
okay.
Recycling some plastics. So it was a nice experience because I knew people that comes from the real experimental world. So I can check my simulation with real experiments. So it was a nice experience because normally you don't have access to the real experiment when you do your simulations. So
Okay.
I'm very glad to
that means you already got quite early in contact with, let's say, interdisciplinary teams and working together in an international environment with a lot of people when you say it was already a European project, right?
Always, because even here, for example, for me, it was like knew all these guys, and there are from Spain, from France, from Argentina a lot, because Mariano is an Argentina guy, of course, and Guillaume a French guy, but also from all the nationalities here in Barcelona Supercomputing Center. But with the European project, of course, there are more nationalities, and it was great because you can see the different point of view, the different realities. It's amazing. I really love that when you perform something very, very international like a European project, because it's not only European, you know, people from all the rest of the world.
Yeah. So how did you then get into the Center of Excellence here, the RAISE project?
So at the beginning, I was not here, if you remember, because I was in another project, but at the end, Guillaume told me that probably I can help in this way, because they are trying to do something about artificial intelligence. I am a computer science guy, so it was the natural way to come to this project. And when Guillaume told me, of course, I wanted to get involved. So I didn't. I decided that I have to. Yeah.
Okay, so do you think AI is more and more impacting this field that you're working on now?
RAISE, of course, and also it was for me a nice thing, because I study. Of course, I study artificial intelligence in my career, but it was a time that I only perform deterministic models that are nice also. But to come back to my root, if I can say that, it was nice, because I could remember all the stuff that I study in my career, and also the new stuff, because right now we have like a jungle of algorithms in artificial intelligence, and right now you have to know which one you have to use. This is the most difficult part right now. No, it was amazing for me. No, so it was natural also.
Okay, and that means also, among all this jungle to use, maybe we can now come a little bit to the topic that you're working on in the project. Yeah, so there is a team of people, of course, working on this topic, right? It's not only you. No,
of course. We have Guillaume, for example, that he is our leader, if we can say that. And also we have a PhD student that is doing incredible work. And we have also the collaboration with the guys from the Riga University. So it's nice. It's a very, very big, big team.
Yeah. And the Riga people, they're not fluid mechanics people, right? Yeah. So
they help us with the AI algorithms.
Okay. Yeah.
Because they are more expert than that in this subject.
Okay. Maybe it makes sense now to dive a little bit deeper in the topic. Yeah. So maybe we can talk about this. I know that you brought a picture, right?
Yeah. If I can share my screen.
Yeah, sure. Okay, what do we see here?
Okay, for example, this is a picture that only to illustrate what we are trying to do. What we are trying to do is to the optimization of a layout of a wind farm. As you can see here, we have a lot of wind turbines. The problem here is that the way that we normally try to resolve this kind of problem is to use deterministic models. So for that, you have to choose the equation that models the partial equation that differential equation that models this physics. And as you can see here in this picture, you have turbulent flows with interaction with the wind turbine. So it's really a big problem, a very big problem.
So what we see here is a result of a simulation, right? This is not a picture that is taken from somewhere. Yeah. So this is something that you ran on a supercomputer, right?
Yes, but this is not my simulation. I have to say that. Okay. So this is another guy's simulation, so that I can have access to this picture, but it's only for illustration, more or less. Okay. Yeah. Because solving this kind of problem is almost impossible using right now, using the resources that we have right now. So we have to use other things if we use deterministic models, of course.
Okay, and I could imagine, I mean, you see the fine granular structures everywhere here, yeah, and this blue dust that you can see that represents the flow field, yeah. It seems quite complicated, these structures, right? And there must be some kind also of interaction between the different turbines, right?
The sizes of the meshes, the models that you have to also join to catch the turbulence. No, it's a nightmare, really. So I think that this right now it's impossible. So you have to do something else. So you have to approximate this probably this solution that is the most real one with another approximation, with another numerical approximation. Yeah.
Okay, so maybe I know you also brought a video. Maybe we can show that.
In this video, this is actually this is our simulation, and this is only the simulation of one wind turbine. And I wanted to show this video because only to show you that for this simulation can take days of simulation, days of using hundreds of processors.
Okay, yeah.
So you can imagine that, and so you can imagine that if you wanted to do that for a farm, and if you have to optimize the layout and you have to change positions, you have to do a lot of simulation with different layouts of the wind farm. So really, you cannot.
And also what makes this very complicated is that it's rotating, right? Yeah, so you really have to deal with moving boundaries in the simulation. So for example, you were talking about these meshes. Yeah, so I know that these meshes are used to discretize the space. Yeah, in the simulation, and everywhere in this mesh you solve your partial differential equations. Yes. But if you then have something moving there, you also have to take this into account, which increases the complexity of the problem, right?
Yes, that's true. Then the problem is that, for example, this is a very good question, Andreas, because there are many ways to solve that. For example, in this case, we are using something that is called a sliding mesh. So we have a mesh that is rotating, so one mesh that is inside another mesh that remains without moving, without another mesh that is moving inside. But you have to do interpolation of the velocities of the pressure. That is a nightmare. So.
Okay, I understand. So you have a fixed mesh on the outside, and you have something rotating on the inside, yeah. And somehow you need to transfer the information from this one from the interface cells that you have here, yeah, in this mesh, to the interface cells that you have here in this mesh, right, which is steady, yeah. Okay. Exactly. And this is done accurately.
So this video is nice. So we have good results. We didn't compare with the experimental ones, but because we decided not to pursue this path, because we have to focus with the AI algorithms because we have a lot of work to do. So we stopped this. We tried in a more simple cases to prove our algorithms.
Okay. Let me come back to the computation complexity. You say you need hundreds of cores to do the simulation. How does this work? I mean, this is one problem you want to solve. How is this then distributed?
How does it work? So this works in parallel, of course. And the problem is that, as I said, so I don't want to enter in details, but because the time steps that you have to put it, so the simulation is very slow. It could take days using hundreds of processors. So I am not using one processor. I'm using hundreds of processors, and even that I have to wait for days to get the right simulation. No, so we have to stop that.
Okay. And there are different kinds of modeling already available for these kinds of simulations, yeah? So that, I don't know, you could have a coarse mesh or a coarser mesh, not simulating all the fine details, and you could have a model that mimics these details, right? What kind of model are you using here? Or is it a fully resolved simulation that you're doing?
In this video, of course, this more or less is full, but our idea is exactly to approximate these results with another model, with another approximation, with a good enough approximation, because we have to get right results, but with an approximation at the end. So for that, our idea was to use surrogate models. So
surrogate models. What are surrogate models?
Okay, the surrogate model, the idea behind the surrogate models is simple. So in this image, you can see that the idea is to replace high-resolution meshes that are close to the obstacle, because normally in the obstacles you have more mesh resolution because you have to get the physics there, no? Because there are in this obstacle, needs to this obstacle pass a lot of things, so you have to catch that. So the idea is to replace these high resolutions meshes that are behind across all these obstacles with a mesh that is a low resolution. This is the main idea. So to replace high resolution with low resolution. Why? Because in this sense we have less elements, and of course the time of simulation can drastically reduce, and also the resources.
Okay, but doesn't this have as a consequence that the results are worse? When you have a model which is running on a lower resolution?
Yeah, of course, always you have to pay the approximation. But the good thing is that we find that because normally in surrogate models you have to put a porosity in this new low resolution mesh to imitate the high resolution models. Okay. So the good thing is that with AI algorithms, this is the good thing about these algorithms, that you can use it to find the best porosity in order to approximate to get a very good approximation of the original problem, if you want, of the deterministic model.
Okay, so you're looking at one single turbine and you're trying to find a surrogate model that is capable of mimicking as accurate as possible the flow, yeah, around this turbine in the wake, let's say, yeah, without using full resolution in this region of the turbine, right? And therefore you're using AI methods, yeah?
Exactly. For the calculate, so because right now the problem is, okay, I want to replace high resolution region with a low resolution region, but you have to put a porosity there in the low resolution mesh. And now the question is, how do I calculate this porosity value or values? Because
yeah,
we can have a tensor porosity, for example. Then we have to use AI algorithms.
Okay, can you say how you get from these high resolution simulations to these AI models?
How I get? So what we are using? So you're talking about the topology of the more or less of the AI algorithms?
Yes, exactly. Yeah. So
Okay.
there's an architecture behind. I know that there are neural
Normally,
networks.
this is something that is already known. So this is not something new about that. But normally, when you are trying with image like that, so if you want to catch the feature of an image, normally you use a convolutional neural network, so CNN. Normally, this is the way that you can really capture the principal feature of an image. So this is the network that we use for the sort of to calculate the velocity.
Okay, and what goes in and what goes out of this neural network?
Yes, normally what you need is, so if you wanted to get what do you want? The porosity value. So what you need as an input is the velocity that are close to the boundary conditions. So this is like our input. Why this region? Because this region is very related to the boundary condition. So it's like more or less the boundary condition, but actually not, because we are using convolutional neural network. We need some image. So we try to get this image that is close to these boundary conditions.
Okay, that means information from an original simulation is the input, yeah, to this training, yeah, and
Yes.
then the network is trained, yeah, and this is done also on high-performance computers. Also, not only the simulation, the training is also done on high-performance computers.
Everything is done with the high-performance computers always. Even the creation of the database is made using a lot of processor, for example, and the training and all the creation of the database and the assignment of a porosity, for example, is doing with GPUs and CPUs. So we are trying to really exploit all these resources that we have here.
Okay, so you have at Barcelona Supercomputing Center, you have a system consisting of normal CPUs, yeah, so everything that the normal user has maybe in his laptop, and GPUs, graphics processing units, yeah, and they are very much suited for AI tasks, right? To do the training. Why is that?
So, for example, in the case of the GPUs, so something that I want to tell you is that right now in Barcelona Supercomputing, we have different supercomputers, one with only CPUs, other with GPUs. And I have to confess that this is right now a problem. But very, very soon we will have Nostrum 5, and we can have the architecture of GPUs and CPUs together. So that will be great, because right now we are using different supercomputers here in Barcelona Supercomputing Center. This is more or less difficult because you have to configure the configurations of each machine is different. So you have to work a lot with the operation guys to say that, okay, I need some libraries, but very, very soon we will have the Barcelona the Mare Nostrum 5, so we can solve this using of these different supercomputers right now.
Mare Nostrum 5 is going to be a pre-Exascale system, right?
Yes.
So do you know how fast it is, or how fast it will be? Do you know when it will be in operation?
I don't want to say that because I don't want to say that because I'm not sure about the details, but I heard that will be Exascale, of course, and that we will have this supercomputer operational in probably next year, I think. So at the beginning of the next year. I hope so. Because, you know, these things are very difficult to plan because you have problems with the fabricant, you have, and you know, right now we have a new things, so you have a new place to allocate all the machines. So we have a lot of problems, what we are solving right now, but we have to wait a little bit and probably next year. But I'm not so sure. You have to ask to the operational, to the guys that works in that.
Yeah, so I understood now. The new Mare Nostrum system 5 will not be in the chapel anymore, right?
No.
Yeah,
no,
so
but
the old one was in a chapel. Yeah, so I visited the old one a few years back. It was very interesting to see. Yeah, it was still very silent inside. Yeah, like you enter a church, and then in the center you have this huge glass cube with the machines inside. Yeah, and it was fantastic in my opinion.
a nice picture, huh?
Yeah.
I think so I visited some supercomputers, and I think that this is the most beautiful one because you have the chapel, you have also this, and sometimes you have also the music from a chapel. Sometimes
Really?
wonderful, yeah. Sometimes they put some church musical, like gospel something, and it's amazing. So you can feel like a magic there. So I will love. Yeah, it was because we have to locate it in another place because we need more space. But is located not so far from the chapel.
And more electricity, right? So there needs to be additional equipment to account for the electricity requirements.
We cannot use the normal sources of the electricity, so they have to put some special things. So it is complicated.
Okay.
But
okay. So what I understood now is Mare Nostrum 5 will be very suited for these kinds of tasks because you have something like a coupled system, yeah? So you don't have separate systems for where you have CPUs and GPUs. You have a system where these components sit together and can be used at the same time.
Exactly. For us, will be easier to work in this platform, but okay. So, but we already have most of the algorithms working, so could be complicated at the beginning because you have to set, of course, all the stuff again. But the algorithms are working, so we advance a lot. So I'm confident that we will able to put in this new supercomputer, and it takes not so a lot of time. I hope so.
Okay. I read some of the papers, yeah, or the work that you're doing, and there's not a single convolutional neural network that you're working on. There are two, right? They interact. Can you explain this a little bit?
And this is, I think, our new way to do the things, because normally people use one convolutional network because if you want to catch the feature of image, that's enough. But in our case, we are thinking in something more general. So we decided to use two convolutional network. Why? I don't want to enter in details, but the main idea is to separate surrogate simulation, so surrogate simulation that costs not so much, from the high resolution simulations. And with these separations, that in the order to have two convolutional neural network, right now we are able also to abstract the geometry of the obstacles. That means that right now we have a model that is capable, if is training in a good way, we can abstract the geometry. So you can have different geometries, obstacle, and the model can work. And
Okay.
also,
So you trade it for one thing and you can apply it for something else.
Yes. Of course,
okay.
you have to have the right database. So this is very, very important. This is the key of the matter always. If you have the bad data, you will have bad results.
And
so
the original database is generated from these high resolution simulations.
You have to use that thinking in a lot of different geometries. You have to train with this in mind if you want to this surrogate model responds well to different geometries. So he can generalize, but you have to train him properly.
Okay, I understand.
Yeah, this is something new, and this is something that I'm proud, because this is a new idea, and we have to publish that because it's a very good idea.
Can you show some results, maybe?
Yes. Only to see very, very fast, as you can see in these slides, you can see that we can catch. This is something that I didn't tell before, but in this slide, you have the high resolution problem at the top and the surrogate model at the bottom. And you can see that the results are very good. So because the approximation is nice, you can see the velocity with the arrows. So for see which how the flow is moving. And also you have the pressure with the blue and red scale. And we can see that the results, the approximation is very good. And with these two convolutional neural network, we can see that we can also approximate different geometries, not only the geometry that I showed at the beginning, but also different geometries that are nothing related with the original one.
Okay, so it's not specific to a one geometry, the trained networks, they're generalizable, yeah?
Exactly. We want to know how far we can come in this way. So it's very, very interesting. So we want to know if the network is capable to generalize no matter what geometry. Could be very interesting. But until now, we have good results. So we think that our new topology is working well, very well.
And as I remember from the beginning, when you were telling, the main challenge is to reduce the computational complexity. Can you say something about how much cheaper now the runs are?
Yes. So from the original one, I don't know, because right now we are not performing with wind turbines. We are only using simplistic geometries. But I can tell you, for example, the difference between how many high resolution simulations we have to do to train in the database versus the low resolutions models that we have to simulate. And is, I think, 10 times. So we have 10 times more simulations in the low resolutions models, in the surrogate models, than the high resolution models. So this is a very good thing, very good feature, because simulations of the low resolution models or the surrogate models are cheaper than much more cheaper than the high resolution. Imagine when we are trying to simulate the real wind turbine. So that will be very, very, very cheap.
Okay. So the project is now running already for 2.5 years, and there is half a year remaining. What is the plan for the half year? So what is missing? What is still missing? What is the remaining challenge that you want to tackle in this half year?
The remaining challenge, so we hope that we can finish, we can prove, because right now these results that I showed before are preliminary ones, because you can see that there are very naive examples, but it's only to see if our algorithms, AI algorithms, are working well, and they are doing. So now we are right now we are trying to work with more complex three-dimensional problems. So with these 6 months that we have, more than we want to really to prove wind turbine. This is because we are not so sure if we can reach the real wind turbine at the end of the project, because it was a really long way. So, but with these 6 months, probably we can catch some wind turbines to see if our model can work in this sense. But of course, right now we are working already with the 3D problems.
Okay. So yeah, because we saw the videos are very interesting. This is all 3D, yeah, and then we saw maybe the results, and they were in 2D, and then there was also a question: what is the input for the training of these convolutional neural networks? Is it 2D data? So sometime before, you use 2D data to get a model that does prediction in 2D, yeah, right? And now you're moving on to 3D, as I understand. Yeah.
Because this is the natural step. We need to, because we want, at the end, we want to be capable to replace a real wind turbine. So
I guess this will make things way more complicated, right? So
yeah,
more compute intensive, because the database you need to create in 3D, yeah, and neural networks also need as an input 3D data, but spit out or 3D also then 3D porosity data, or what does it then?
Yes, and the problem is not only I didn't say that, but the problem is not only the 3D problem, the 3D geometry, but also because we are dealing with not with an static problem. We're dealing with a problem that is dynamic. So that will be I think that will be the real challenge. Is to catch the dynamic features, because this is not an image really. It's like a video that we have to catch the features that we have.
Yeah. And
we're working on that.
Since you mentioned dynamic, yeah, so the models that you have, they can also react on different inflow conditions. Yeah, so
yes,
if you have, so later on, it would be the ideal case that you have a whole wind farm and you put up these wind turbines, yeah, and you try to optimize the whole wind farm, and you put these surrogate models in. So there will be different for the different wind turbines in the wake of the upstream wind turbines. There will be different inflow conditions, right? So they have to react to that, these models, and that's also a big challenge, right?
So this is the big challenge right now for me. Yes. Right now, we are capable of assign a porosity dynamically in time on execution time. But this is different because right now we have to catch features not from an image, from a lot of images that came previously. So this is the really dynamic part that we have to deal. And we are working with the Riga University. This is a challenge because we have to use, maybe we have to change, we can preserve the topology of our convolutional neural network, but we have to add more AI tools. Yes, probably.
So this sounds like this can revolutionize the field of optimizing wind farms, right? So is there already some kind of interest from the industry?
Okay, I hope so. So that depends of the guys from the industry. We are offering a new way to solve that is cheaper than to make, of course, all the simulation that maybe it's impossible. There are other options, but surrogate normally is the best way of approximation. I hope so. Yes, this is our main objective, to attract the industry, the science, to say, hey, I have a new option. You can prove. This is a framework, so we already proved, so you can try. So this is the goal.
Okay, and from that on, there could also be in the future some societal impacts. Yeah.
So and not only me. So this is the nice thing of this project. So we are dealing with real problems. Real problems in engineering, it's very complex to solve. Sometimes it's impossible. So we are offering solutions in fields that probably we don't have. So I'm proud of that. So probably you, because offering these kind of solutions is very nice. And also I have to say that RAISE is not only, I'm talking about my things, about physics, about the models, the algorithms, but also there are guys working on how to store all the data that we have to generate, also guys that are working on how to configure, how to do the configuration of all these super machines that we have to use. So it's a framework that we are doing here. So nice work.
So I have the feeling you're very motivated and enthusiastic to work on this project, and you really enjoy that. But I could imagine it's also a lot of work. Yeah. So do you have time to relax, and what do you do during this time?
You know that, of course, this is something that I really love, and I really love to work. So for me, this is the good thing about for me about science. So when Monday comes for me, it's not so a big deal because I really want to work because I have a lot of things to do. So nice, but of course we have to do other things. For me, swimming is the best idea for me. For me, this is my way to escape of all these things that are beautiful but complex. So to escape a little bit, to relax your mind. So I swim a lot, and I hope to swim until my death. So because I really love it.
Okay, so that's something that you do over at the weekend, yeah?
Not the weekends, even in the week. So when I find some hour that I can use in the middle of the week, I used to swim.
So
and
you
then
also
back to work because it's a good thing to unplug a little bit, and then you can reconnect with new ideas. Something that is very curious is why I swimming. Normally I think about things. So because you are swimming and you can think about, hey, this idea could be nice. It's not only swimming. I can think in all the things that are around me. Work also.
So you also have flexible working times, yeah? So in between the work, you can decide, I now go swimming.
Yes, this is also a good thing about science for me. You have flexible schedule, so you have to decide. You can decide. Of course, sometimes I have to work some weekends because we have to finish something, but also I can take 1 hour from a day to swim. So I fix everything to schedule with the work week for swimming, and also to do other things. For example, I love to go to the cinema. So for me, it's to see films. It's a relaxing thing. So, but swimming is my thing, I think.
And I guess you also sometimes visit your family in Ecuador.
Yeah, but the visit my family is complicated because they are the other side of the ocean. So it takes me, it takes a lot of travel, so more or less, I calculate that when I leave Barcelona from door to door, so to leave my door in Barcelona to get my door in Ecuador, it takes me 24 hours, so 1 day.
Oh, wow. Okay.
But each time I can, so probably once a year, I try to, because I miss a lot my family.
Something for the vacations, right?
Yeah, and of course. Yeah. And that my city is in the middle of the mountains. It's a beautiful city. This is my city. That this is a beautiful city. We have amazing food.
Yeah, that's true. Yeah.
So Ecuador has amazing food. We have a lot of land. Especially, I think the landscape in my country is amazing because here in Europe you have wonderful towns and small towns, but I think that South America has the most beautiful landscape in the world. This is my opinion.
Yeah, I really enjoyed that. Yeah, I have to say.
I'm glad that you joined the
very green. Yeah, so I was surprised when we landed with a plane how green everything is. It was very nice.
Yeah, because my city rains a lot, so this is a green city. We have a lot of parks with a lot of trees. I miss that a lot. The mountains and the trees, the green.
Okay, Cristóbal, I think I mean I could talk to you forever, yeah, and we should continue next week when we meet actually in Iceland, the online meeting. But yeah, we have to stop now. Yeah, we have to come to an end. So I really enjoyed talking to you, and I hope the audience, they got some good insight in the work that you're doing here in the project, Barcelona Supercomputing Center in general, and also together, yeah, which seems to be quite important. As you said, you like to work in an interdisciplinary setup to work with the computer science and AI specialists from the Riga Technical University. Yeah, so I learned a lot, and I hope everyone else also learned a lot. And with this, I would like to thank you and all the audience. And if you like, yeah, please give us a thumbs up and subscribe to our channel. Thanks, Cristóbal, for being here.
Thank you. It was my pleasure. I really love to talk, as you can see. So whatever you want, we could do another interview.
Thank you. Bye-bye, Cristóbal.
Bye.